In this video, we'll be learning how to solve a three-variable system by utilizing the substitution strategy. So substitution in three-variable systems can be a little bit more complicated than elimination, but where it's really helpful is when we have equations, where we have three equations where maybe a variable is missing in some of the equations. So you can see here that we have three equations. One has three variables, one has two, and one has one. And in a case like this, substitution is actually our best choice because we've already been given one of the values. And if we use this value very strategically, we'll be able to work backwards and find all of the other values. So here we're going to use substitution because we have equations that are missing variables. So if you look here, we already know that in our ordered triple that's going to be our answer, that our z value is equal to 5. And because our z value is equal to 5, we can actually take that z value right away. And I suggest if you know one variable and you see a two-variable equation, take that variable value and substitute it in for z. So here we now have y plus 2 times 5 is equal to 13. And what we notice is that equation, because we used substitution, one of the variables has disappeared, and we're left with y plus 10 is equal to 13. Subtract 10 from each side, and y is equal to 3. So already in just a few seconds, we've found our second variable, and we know that the y value for this ordered triple is equal to 3. And then we can use substitution again and say, well, we know what y is equal to, and we know what z is equal to. So if we substitute those in for y and z in that third equation, so we have 2x minus 3 times our y value is 3, plus our z value of 5 is equal to 10. We notice that by utilizing substitution, we now have an equation that only contains one variable. And so we can solve for that one variable. So we have 2x, I'm going to use keep change here, so plus a negative 9, plus 5 is equal to 10. So we have 2x plus negative 4 is equal to 10. Add 4 to each side, and we end up with 2x is equal to, that's an addition there, 14. Divide by 2, and we find that x is equal to 7. So I have now solved my ordered triple and found that the x value that I need for this ordered triple is 7. So here we have an x value of 7, a y value of 3, and a z value of 5 that will make all three of these equations true. So again, substitution is really helpful if we have a variable missing from any of our equations. So here in example 2, you'll notice again that we have an equation with one variable that is missing. We're missing our z value here. So what we're going to do is we are going to utilize substitution here simply because we have that one variable missing. You can use elimination, but I really like substitution because I think it makes things a little bit easier. So we're going to start off just like we did with two variable systems. We're going to focus in on this equation here and figure out which variable we can solve for by itself very easily. And what I notice is if I subtract 2y from each side, I can easily get my x value alone. So it's x is equal to negative 1 minus 2y. So I can get x alone very easily, and I can see that x is equal to negative 1 minus 2y. So what I can do is I can take what my x value is equal to, which is negative 1 minus 2y, and I'm going to substitute it into the other two equations. I have negative x, and then plus 3y plus 2z equals negative 4, and I have negative x plus y minus 4z equals 10. So I'm doing something very similar to when I did elimination. I'm basically mixing equations 1 and 2 together, and then equations 1 and 3 together. But I'm utilizing substitution instead. So we're going to substitute what our x value is equal to into the other two equations. So here, if I take negative 1, remember there's a negative 1 in front of here, negative 1 times what x is equal to, so negative 1 minus 2y plus 3y plus 2z is equal to negative 4. I have now used substitution and created an equation that only contains two variables. So I'm going to simplify this here. So distribute. So I have 1 plus 2y, and then plus 3y plus 2z is equal to negative 4. Then I'm going to combine any like terms that I see. So here I see 1 plus 5y plus 2z is equal to negative 4. And then I'm going to subtract that 1 over. So I have 5y plus 2z is equal to negative 5. So I've taken what x was equal to, substituted it into equation 2, and found a new two-variable equation. So now I'm going to do the same thing down here with equation 3. So this is mixing equations 1 and 3 together by substituting with equation 1. So I'm going to, again, remember there's a negative 1 here. So I have negative 1 times x is equal to negative 1 minus 2y plus y minus 4z equals 10. And then from here, I distribute. So I get 1 plus 2y plus y minus 4z is equal to 10. And then I add my like terms together. So I have 1 plus 3y minus 4z is equal to 10. Subtract the 1. And I have 3y minus 4z is equal to 9. So here's my second equation. So now we're in the same spot that we were when we utilized elimination. We've used a strategy, in this case substitution, to mix the two equations together so that we get two variable equations. And now what we're going to do is we're going to mix these two equations together and use another systems solving strategy. So we have 5y plus 2z equals negative 5, and we have 3y minus 4z equals 9. Now, in this case, now that we've gotten it down to two variable equations, you can use whichever strategy makes the most sense. So here, if I look at this system in red, to me, substitution doesn't make sense because I would get some nasty variables. So I'm going to use elimination here. So I'm going to multiply through this top equation by 2 so that I can get the z's to be a positive 4 and a negative 4. So if I multiply through that top equation by 2, I end up with 10y plus 4z is equal to negative 10. And then from here, we add these two together. So I end up with 13y is equal to a negative 1. And then from here, I divide by 13, and I find that y is equal to a negative 1/13, which if we use our calculator, is equal to approximately a negative 0.08. So there we have finally found our y value. So now that we've found at least one variable value, we're going to work backwards and find our z value and our x value, just like we did in elimination. So here we're going to take that y value, we're going to go back to one of our two variable equations. So we have 3y minus 4z is equal to 9, and we're going to substitute y in there. So we have 3 times, I'm just going to use the decimal approximation, negative 0.08 minus 4z is equal to 9. So then I have negative 0.24 minus 4z is equal to 9. Add 0.24 to each side. So I have negative 4z is equal to 9. Divide by negative 4, and I find that z, in this case, is equal to approximately about a negative 2.31. So now that I have two variable values, I have y and z, I'm going to take both of those, go back into an original equation, and it doesn't matter which one we pick, so I'm just going to pick this one right here. So I have negative 1x plus y minus 4z is equal to 10. And I'm going to substitute those two values in there to find my x value. So I have negative 1x plus a negative 0.08 minus 4 times a negative 2.31 is equal to 10. So I have negative 1x plus negative 0.08. And then I'm going to use keep change here. So I have negative 4 times negative 2.31, which becomes a positive. And then 4 times 2.31 is 9.24. And that's equal to 10. And then I can combine those together. So I have negative 1x plus 9.16 is equal to 10. Subtract 9.16 from each side. So I have negative 1x is equal to 0.84. Divide by negative 1, and I find x is equal to a negative 0.84. So at this point, I now have my ordered triple. So I have an x value of negative 0.84, a y value of negative 0.08, and a z value of negative 2.31. So you can see here that sometimes they won't be very nice numbers. Sometimes they will be decimals, and you have to be prepared for that and okay with that because it's the exact same process. So for this last example here, I do want to show you how if we have 3 variables and 3 equations, we also can utilize substitution if it looks appropriate for the situation. So here you'll notice I don't have a missing variable, but substitution will still work. And if you're going to use substitution, what I suggest you do is take a look at all 3 equations. We have equation 1, equation 2, and equation 3. Take a look at them and decide which one you could solve for one variable alone really easily. And what I notice is in equation 1, I can get x alone pretty easily if I just add 6y and add 2z to each side. So that's what I'm going to do. I can get x alone and say x is equal to negative 8 plus 6y plus 2z. So just like with 2 variable systems, we get that single variable alone. And then just like we did on the previous slide, we're going to take what x is equal to here, which is negative 8 plus 6y plus 2z, and we're going to substitute it into these other 2 equations. So we're going to substitute it in place of x in the other 2 equations so that we create 2 new equations that only contain 2 variables. So I'm going to start off here by combining equations 1 and 2. And I will tell you this is going to be a little bit of work with having 3 things to substitute in. So I take a negative x and I substitute in negative 8 plus 6y plus 2z. And then I have plus 5y plus 3z is equal to 2. And then I distribute out that negative 1 to all 3 items. So I have 8 minus 6y minus 2z plus 5y plus 3z is equal to 2. I then want to combine my like terms. So I see a negative 6y and a positive 5y. So I have 8 and a negative 1y. Then I have 2z and 3z, so I can add those together to be plus 1z is equal to 2. And then from here I'm going to subtract the 8 over to get the numbers together that do not have variables. So I have a negative 1y plus 1z is equal to negative 6. So I have substituted x into that second equation, and I have created a new 2-variable equation. Now from here I'm going to do the same thing on the other side, but I'm going to use equations 1 and 3. So I'm going to substitute what x is equal to into that third equation there. So I have 3, and then in place of x, negative 8 plus 6y plus 2z. Then I have minus 2y minus 4z is equal to 18. So now I'm going to distribute that 3 to all 3 items. So I have negative 24 plus 18y plus 6z minus 2y minus 4z equals 18. Then I combined my like terms, so I'm going to start with the negative 24 is still by itself. I then combine the y's to get a plus 16y, and I combine the z's to get plus 2z is equal to 18. Then add 24, to get 16y plus 2z is equal to 42. So here I have a second equation that contains two variables. So now I can bring these two together, just like I did with elimination. We're going to bring these two together, and we're going to create a two-variable system here. So I have negative 1y plus 1z equals negative 6, and I have 16y plus 2z is equal to 42. So here you can utilize elimination, or you can utilize substitution again, because I can see that I could really easily get this 1z value by itself. So that's actually what I'm going to choose to do here. I'm going to choose to get 1z by itself by adding 1y to each side and finding that my z value is equal to negative 6 plus 1y, and then substituting what z is equal to into this other equation. So utilizing that substitution strategy again to help us solve for a single variable. So here we have 16y plus 2, and then z is negative 6 plus 1y, and the whole thing is equal to 42. So I distribute, so I have 16y plus negative 12 plus 2y is equal to 42. I then combined my y's together to get 18y minus 12 equals 42. Add 12 to each side, so I find 18y is equal to 54. Divide by 18, and I find that y is equal to 3. So I have now found my first variable in this ordered triple. So now I'm going to do just what I did before. I'm going to take that value of y and I'm going to plug it back into one of my two variable equations. What I notice is if I plug y into here, this is a pretty easy equation to work with. So I have negative 1 times 3 plus 1z is equal to negative 6. So here I have negative 3 plus 1z is equal to negative 6. Add 3 to both sides, and I find my 1z is equal to negative 3. So I now have two of my values. And then I'm going to go back and I'm going to utilize one of my equations at the top. What I'm going to utilize here is this nice equation right here, because my last variable that I need to find is x, and that equation will give me x. So x is equal to negative 8 plus 6y plus 2z. So I have x equals negative 8 plus 6 times my y value of 3 plus 2 times my z value of negative 3. So I can keep going. So that's plus 18 plus a negative 6. So negative 8 plus 18 is going to give me 10 plus a negative 6. So that means x is going to equal 4. So I now have found my ordered triple of x is 4, y is 3, and z is negative 3, and that contains the values of x, y, and z that if you take them and put them back into all three of these original equations, all three of those equations will be true.